Hi, I'm Romain Loiseau, and I'll present our work about fast segmentation of LiDAR time sequences. Most methods consider the rotating LiDAR data as a discrete sequence of frames, corresponding to full rotations of the sensor. The idea of this paper is instead to split the sequences into slices of acquisitions covering a fraction of rotation. Since slices are acquired faster than frames, our model achieves a reduction of over 5 times in terms of latency and 50 in model size, while reaching accuracy on par with the best segmentation algorithms. To precisely assess the real-time readiness of LiDAR segmentation methods, we also introduce HelixNet, a 10 billion points dataset with fine-grained timestamps and sensor rotation information. Real-time analysis of 3D data sequence is crucial, as LiDAR sensors are becoming prevalent in autonomous driving. However, LiDARs have a complex acquisition geometry, as the sensor is rotating at the top of a moving vehicle and scans a dynamic world. Most methods split the acquisition into sensor rotations or frames. This leads to an unavailable latency of 100 milliseconds, which corresponds to the rotation frequency of the sensor. This latency corresponds to 1.5 meters at 50 kilometers per hour, and we have to add the inference time to get the full latency between the acquisition of the first point of the rotation and the prediction of its label. With over 1 million points per second, real-time processing remains a difficult challenge for LiDAR sequences, as the number of acquired points often results in prohibitive latency for autonomous driving. To precisely assess the real-time readiness of semantic segmentation methods, we release HelixNet, a dataset for online segmentation of LiDAR sequences. This dataset is the largest open-source Velodyne dataset with 10 billion annotated 3D points across 6 French cities in various urban settings. This dataset contains crucial pointwise information. Specifically, we provide the release timestamps, the sensor rotation, and the sensor position for every point. The specificity of our dataset enables a realistic slice splitting and online inference. To process the data, other methods use either range images, 2D polar grids, or 3D partitions. But because of the sensor movement, both polar and cylindrical partitions are approximations. We propose to split the acquisition into slices of rotations. Taking the complex spatio-temporal structure into account results in a much smaller acquisition latency, leading to real-time online semantic segmentation. We present Helix4D, an efficient spatio-temporal transformer, for processing a sequence of slices. Our model resembles cylinder 3D in the sense that it uses 3D convolutions on cylindrical grids of decreasing resolutions. However, since we only process slices and not frames, we can simplify the architecture to its bare essential. Furthermore, at the innermost layer, we use an efficient sparse spatio-temporal transformer that performs attention on voxels from both current and past slices, with a learned spatio-temporal relative positional encoding. The transformer gathers information on a large spatio-temporal receptive field while remaining efficient, as the encoder is performed only one per slices. With this architecture, we achieve state-of-the-art performances with a reduction of over 5 times in terms of latency and 50 in model size. We evaluate various state-of-the-art models in both the frame-by-frame setting and with slices of 1/5 turn. We see that while our model is comparable to state-of-the-art on the frame-by-frame setting in terms of precision, we achieve real-time LiDAR semantic segmentation while keeping the same performances when reducing the slice size, while always having inference time accordable with real-time setting. Looking at the results for several slice size, we see that Helix4D is as accurate as the largest and slowest models with an inference speed comparable to the fastest, less accurate models. To conclude, we presented both a dataset designed for methods real-time readiness assessment and an efficient spatio-temporal transformer architecture designed for rotating LiDAR sequences. We achieve state-of-the-art performances for semantic segmentation with a reduction of over 5 times in terms of latency and 50 in model size compared to others. Thanks for your attention.